Warahmatullahi wabarakatuh and salam sejahtera. This is an example of the ideal Otto cycle. Ideal Otto cycle has a compression ratio of 8. At the beginning of the compression process, air is at 100 kilopascal and 17 degree Celsius and 800 kilojoule per kilogram of heat is transferred to air during constant volume heat addition process. Sketch PV diagram and determine maximum temperature and pressure that occur during the cycle, the net power output, thermal efficiency and mean effective pressure. So, first thing first, this question asks us to sketch the PV diagram. So, this is the PV diagram for the Otto cycle. Okay, this is the compression, isentropic compression. This is constant volume heat addition. This is isentropic expansion, and this is constant volume heat rejection. You have to know this. Okay. At V1, this is V maximum. V1 is equal to V4. And at state 2, this is V minimum. Okay, V at TDC and V at BDC. V2 is equal to V3. Given here, RV is equal to 8. And RV, which is compression ratio, is by definition is Vmax over Vmin. So Vmax is V1 over V2. As I mentioned, V1 is equal to V4 and V2 is equal to V3. So the question asks us to find the maximum temperature and maximum pressure. So we do the process for process by process. At process 1 to 2, this is isentropic compression. Given here, P1 is equal to 100 kPa. Temperature is 17 degrees Celsius. So I convert degrees Celsius to Kelvin. Since the process is isentropic compression, then I use formula hijau. Okay, so in this topic, the formula hijau given here. Okay, the relation between temperature and volume. So this is formula hijau, and I use this formula hijau to find T2. Given here K, and the substance is air, therefore K is 1.4. Alright, so I get T2 is equal to 666.207 Kelvin. 2 to 3 is constant pressure heat addition. So given here, Q in is 800 kilojoule per kg, and I have a formula Q in as a CV T3 minus T2. Why I use CV? Because this is constant volume. From table A2, CV is 0.718 kilojoule per kilogram Kelvin. So I put all the value and I get T3 as a 1780.41 Kelvin. So T3 is the maximum temperature. To find P, before I forget, okay, to find P2, okay, here this is P2. Okay, P1 and P2, I use the ideal gas equation. P1 V1 over RT1 is equal to P2 V2 over RT2. So I get P2 as this formula. Okay, V1 over V2 is 8 and T2 over T1 here. Okay, then I get P2 as a 1837.812 kilopascal. Okay, next we go to the P3. So P3, I relate state 2 with state 3. Okay, P2 over P2 V2 over RT2 is equal to P3 V3 over RT3. Okay, so V2 and V3 is the same. So I can cancel V2 and V3. Then I will get P3 as a 4.911 megapascal. So this is the highest pressure. Okay. 3 to 4, if you can see from this PV diagram, this is isentropic expansion. Since this is isentropic expansion, then I can use formula hijau that relates T and V. Okay, then from this formula, I get T4 as a 774.96 Kelvin. And I get P4 from the formula ideal gas equation. Okay, then I get P4 as 267.60 kilopascal. So this is the question A. Question B is net work output. So W net given here as a Q in minus Q out. CV, okay, I put the big bracket here. T2 minus T3, this is for Q in. And CV T4 minus T1, this is for Q out. Then I get W net as a 451.791 kilojoule per kilogram. Next question is thermal efficiency, and the formula is W net over Q in. So I get the W net here, the value is here, and Q in is CV T3 minus T2. Please don't forget to put CV here. Okay, then the thermal efficiency is 56%. Next question is mean effective pressure. The formula of mean effective pressure is W net. This is small letter, okay, divide with specific volume maximum, which is V1, multiply with 1 minus 1 over compression ratio. So how to get V1 or V at BDC or V maximum? I get from ideal gas equation. So from ideal gas equation, I get the specific volume is 0.8323 meter cube per kilogram. Therefore, I put this value here. Then I will get mean effective pressure as a 620.337 kilopascal. Thank you.